Thank you, Marie-Therese, and thank you all for the nice invitation to this beautiful place here. It's the second time I'm in Lumini now, and I really enjoyed it. And today I'm going to speak about this new traffic flow model, which is a joint work with two of my colleagues from Mannheim, Jan Friedrich and Oliver Kolb, and two further colleagues from Nice, which are Felicia Chiarello and Paola Nuatin. So what you see here is the beautiful castle of Mannheim. So Mannheim is located in the middle of Germany, and we have this nice castle. And as you may imagine, the math department is not inside the castle. It's a bit outside, but anyway, the castle is covered by all the economists, and we are allowed to give lectures there. Okay, I want to show, or I want to present a model related to a non-local structure, and I first want to give you some impression how such a model may look like. So let's start in general with these non-local systems of capital N conservation laws that might have the form as given by Formula 1 here. And what you see is we have some quantity u from Rn, and we have some flux function of this type of dimension. And you see here the flux function, there's a convolution inside. So and now there are a lot of examples which fit into this context, but I want to try to focus on the topic of this conference here, which is related to crowds. So, and I found one nice statement as an interpretation for this kind of equation, which is the non-local nature of equation 1 is suitable in describing the behavior of crowds, where each member moves according to his evaluation of the crowd density and its variations within her and or his horizon. So this statement is taken from a paper by Agarwal, Colombo, and Guatin, and which fits into the context or the meaning of what we understand about the movement of crowds, let's say. So, and there are a lot of applications related to moving crowds. I want to mention the applications since 2010, and I want to focus really on the crowds, and crowds means, for example, and as you can see here, the first reference, which means crowds or pedestrian dynamics. There was work by Rinaldo Colombo, Garavello, Lecoureux, Mercier, and so on in 2012, where they came up with a system of conservation laws for moving crowds involving such an interaction as a non-local term. Then there are works related to supply chains, again by Rinaldo Colombo, Michael Hertie, and Mercier, where they considered a supply chain with a different non-local structure related again to this kind of equations. Then there's a material flow on conveyor belts related to pedestrians in some sense, where you consider some moving elements or objects lying on some conveyor belt and needs to be transported from one place to another place, where we had real data from the engineers and could do some model fitting as well. And let's say the traffic flow. So what do we mean by non-local traffic flow models? So in the non-local case, I want to restrict to the scalar case only and say that non-local traffic conservation laws are now of this kind of equation, so some conservation for the density rho, which means we now have a flux function, small f, where this convolution is again involved in some sense, which I will explain in a few minutes, and we are purely scalar in the case that all the variables are from R. So, and there there has been done a lot of research since 2015, let's say, on this special kind of non-local traffic model. And let's go through step by step. So the existence and uniqueness of this kind of equation was done by Amorin, Colombo, and Teixeira in the first work in 2015. And then 1 year after, Blandin and Goatin started to do the modeling and the numerical analysis in the special case of a non-local traffic model, which I will also explain in a few minutes. Then there was some work done on higher order numerical schemes by Charlon, Goatin, Villada, or Friedrich and Kolb, where they applied sophisticated numerical methods to really resolve the convolution terms and the dynamics driven by the convolution. Then you may also consider, as we have seen in many talks, these micro to macro limits, also done by Goatin and Rossi, or Ritter and Shen. I was paid by Paula to mention her so often. And of course, one question that arises when you start to study these non-local equations is there any convergence to the classical LWR model? Okay, or are these really different types of model for the traffic evolution? So, and for the convergence, this is a very recent topic. There are works by Maria Colombo, Crippa and Graf Spinolo from this year, and Keimer and Flug also from this year. But the assumptions are very strict, so let's say in general you won't observe the convergence so far. So, but now let's go into the modeling, and let me go through. I want to explain now two models, the one by Paula and Blandin, and the other one we did afterwards. So let's assume in this segment of road, or one segment of road, and you sit in this red car, and what you see in front are these yellow cars. Meaning that you have something like a fixed horizon, which you can observe sitting in your own car. So, or in other words, drivers adapt the velocity to the downstream traffic, okay? And what you can see here, this eta, might be the horizon you are able to observe. Okay, and what's also important is that the closer vehicles in front of you are more important. So, and the common approach, or the first approach, was the velocity of the mean downstream traffic to consider and to model with the help of the flux function. And the new approach, as we will see, is instead of considering the mean downstream traffic or downstream density, to really use the mean downstream velocity instead, okay? So two different issues for the modeling so far. And I will go through and explain you both in the first part of the talk, and in the second part I stick to one model only and try to explain how we now we are able to extend this kind of modeling to a first network situation. So I start with a model by Paula for the mean downstream density. So we have the density of cars, and the density of cars has an upper bound, which is rho max in this sense. And now we try to fill in the missing parts of the conservation law. As you can see here, there's a lot of space. And we assume that drivers adapt their speed based on a mean downstream density, as I told you, which might result as the convolution. The convolution you can see here, this corresponds to the mean downstream density. And the convolution you see is now defined by this integral here. And we additionally add this g of rho to complete the flux function, and in case of traffic, we choose g of rho equals to rho. But in general, we might also this more generic expression g of rho. So, and then under the following hypothesis, you can show the existence and uniqueness of weak entropy solutions. What do you need for that? You need, of course, first some initial data, which should be of bounded variation. And you need assumptions on the functions g and the velocity v. So g should be a C1 function and v should be C2. And furthermore, v prime should be smaller than or smaller equal than 0. So, and for the kernel itself, you need that the kernel is a C1 function, also that w prime is smaller equal than 0, and the integration should be some value w0, and here if you consider the limit, this expression should hold. So, and under these assumptions, you are now able to show the existence and uniqueness of weak entropy solutions for this kind of model, which is done in this reference you can see here. So now I try to explain what's the difference to our new approach. And as I told you, we say that drivers adapt now their speed based on a mean downstream velocity. What does it mean exactly? So as you can see here, it means that the flux functions, especially the convolution here, changes. So, and let's translate mean downstream velocity in terms of some mathematical expression now is to say the convolution is now here given by this expression and inserted in the flux function, g of rho is as before. So it's a different way of expressing the observation you did before. So, and of course, we need some conditions to show the existence and uniqueness for this special kind of model. And here we have additionally that we assume that there's some interval I given by an upper bound rho max, and we additionally assume that g prime is smaller equal than 0. But anyway, as for traffic holds that g of rho equals to rho, this is fulfilled. So, and now what we can do is, for example, to say that in case of a linear velocity function, v of rho, as it is usual in traffic, for example, the model given by Paula coincides with the model we have proposed here. Okay, for linear velocity, you can use either model 1 or model B2. So, but the advantage here is maybe that with a new approach, you may also cover changes in the velocity function as well. And what I'm going to show is, for example, in the case we would have nonlinear velocity functions, the models do not coincide and will reflect another dynamical behavior. So first of all, under the assumptions I have shown, we are able to prove existence and uniqueness of the new model as well. And you see that the solution itself will fulfill a maximum principle. And I don't want to go into the details of this theory, but what we do here is we do not use a Lax-Friedrichs type discretization and then do all the estimates to show the well-posedness of the model. We decided to use a Godunov type numerical scheme to prove all the estimates we need for the well-posedness, which means we can derive, based on these Godunov type schemes, these L-infinity bounds, bounded variation estimates, and then show that the sequence of approximate solutions really converge to our weak solution. So, but as I told you, I do not want to go into the details of the proof, but I want to show you maybe the key idea of this new numerical approach. So, and what you see here is the discretization of these road segments in terms that we are able to use a finite volume scheme like the Godunov one. You see here the cell averages, and you see the discretization in this terminology here. We have this xj cell centers, and we have a spatial step size h with n times h equals to eta, which was the kernel, and eta is some natural number. We have a step size tau, and we have the crit constant lambda defined like this. And we want to set up now the Godunov type scheme. So the crucial point is here, of course, the evaluation of the convolution. So it's not standard, so we are not apply directly, or cannot apply directly the Godunov type scheme we already know from the local case. We have to be sure that the convolution is really exactly evaluated. So, and if you look at the convolution, which is shortly given here in this kind of notation, you see the crucial, or the main ingredient is now here to look at the interfaces of this discretization and to evaluate the convolution in the right way, given by this kind of quadrature rule we derived here, where you have some weights gamma k, and where some example is given here. So for example, let's assume the capital N equals 2, so there are two neighboring cells influencing the convolution. So here in blue given, you really get the impression what is the necessary discretization in this special situation for computing the convolution. So once we are able to compute the convolution, we now have to set up the scheme, which means we have to think about the right numerical fluxes of the Godunov scheme. And what we see here, setting up the flux, which means, again, we have these two cases to distinguish the minimum of this type and the maximum of this type. And doing the convolution evaluation, we see that the flux function reduces to this kind of expression, meaning that the Godunov type scheme we derived here may correspond to an upwind scheme only, okay, to the idea of upwind. So what else is missing? Of course, the initial data we have to integrate over the cell, and then we have the full scheme given by this iteration here, where now the flux and the convolution are directly evaluated. And based on this kind of iteration, we now did all the proofs for the well-posedness, meaning that there is some CFL condition we have to take into account since we are in this hyperbolic setting. And the CFL condition is given by equation 6. You can see here, you see there's some V prime involved and some G prime. That's why we had these assumptions on these two terms, or two functions here. We can show that under the CFL condition, the maximum principle is satisfied for the numerical discretization we have proposed. And we can additionally show that there is this discrete BV estimate given by this guy here, where this rho bar is exactly the solution we obtained from the numerical discretization. Okay, so we are fine so far with a proof of existence and uniqueness. And we are now able to do numerical simulation based on this scheme. So, and what I want to show you here is to consider the traffic example. As I told you, G of rho reduces to rho. And we use some nonlinear velocity function. So 1 minus rho to the power 5. Some kernel given like 1 over eta. And the initial conditions given in this picture here. You see constant initial data here with a peak between 1/3 and 2/3. Eta is 0.1, and the final time horizon is rather small. But as we can see now, or in a few minutes, this is just to give you the right impression of the solution. So now we are interested in the following points here. We'd like first to compare the models proposed by Paula and our approach to really show how they differ, okay? As I mentioned earlier, for linear velocity functions, we know that these two approaches are the same, and now we want to point out the differences. And the second question we try to answer is what happens in the limit case, okay, for eta to 0. So we try to go back from the non-local behavior to the local one, at least from a numerical point of view. So let's start first with the model comparison. What you see here is now the initial data and the solution in red given by the downstream traffic density proposed by Paula. So it's slightly oscillating, as you can observe here. And here now the solution we are able to propose with a new model and blue. And what we see is that the solution we propose, the model we propose, results in a solution that is, let's say, more monotone. So we avoid these large oscillations, but we resolve the traffic jam in a different way. So this is now, at first, one observation we did, okay? I don't want to talk about the quality of these two kind of models. It's just to give you an impression how they may differ. So, and for the numerical convergence, in the case of eta to 0, we have to do the comparison to the classical local LWR model as given here. What we did now is to consider different kernels. I hope you can see it. So the first type is eta equals to 10 to the power minus 1, which results in this smoothed out picture. Then we add eta 10 to the power minus 2, which is getting closer to the local solution of the LWR model, and so on. And finally, in red, you see what happens for 10 to the power minus 4. And surprise, surprise, it's very close to the solution we really get from the LWR model. Okay? As I told you, there are now some recent results for the proof of this kind of convergence, but for very strict assumptions, okay? So usually we don't fulfill all these assumptions, but we observe the convergence, but we are not able so far to prove it rigorously, okay? It's just a numerical observation. So, and you see here some measurements in the L1 distance for this kind of approximation, and you really see here how the L1 distance decreases for this kernel, for these smaller kernels. So then we had the idea to extend these models to networks, okay? Networks in the sense of that we are really compute large networks of traffic roads, and okay, it's very ambitious to do that. That's why we decided first to think about the connections of the models for a one-to-one junction only, okay? So what does it mean? So maybe you're familiar with traffic flow networks. The setting is given by some conservation laws of this type of form, so of LWR type, for example, on each road segment. And then the modeling point is, of course, how to connect all these different kinds of conservation laws at intersections, in the sense that flux is the conservation of mass is still true, okay? So, but this conservation assumption leads you to different coupling conditions, resulting in as a boundary value problem for this type of conservation laws. So, and this is done now for many years, and there's a nice book by Coclite, Garavello, and Piccoli, where this framework is explained for the local type of traffic flow equations, okay? This is well investigated and well understood, I would say. So, but what happens if we try now to extend the non-local equations to the networks? So what we aimed to do, or the intention was to consider different road segments where you have different velocity functions, of course. Yeah? And in the case, we would restrict to the mean downstream velocity model, which was the second one I introduced, is now that the flux function is a composition of two parts, namely the part from, let's go back to the picture here, the part which is related to road 1 and a part which is related to road 2. Okay? Just to give you a rough picture of what there's maybe behind. And what you see here now, the g of rho, which was one component of the flux function, is now only influencing the second type, or the second road segment, in the sense that g of rho should be the minimum of rho and rho max, so maximal density of the second road. And this results in two types of convolution given by these two expressions here now, where we also consider these two types of velocity functions for these two roads. Okay. So, and again, this eta represents the look-ahead distance we have, so the drivers we can observe.
Can you see what is the dependence of omega eta with respect to eta? So it's something which is integral 1 all the time, the omega eta. Because you said what happens when eta goes to 0. What is omega eta?
Yeah, it's something like a delta. Yeah? Yeah, yeah. Right, yeah. Okay, so then again the model assumes that drivers adapt their speed based on a weighted mean of downstream velocities as before, now modeled in a different way probably. And what we also observe is for the velocities, V1 equals V2 and the same different capacities of the road, that the model coincides with the one we proposed for a single road segment only, okay? So now the picture I showed you for the model before results in a new picture given like that now for the intersection of these two roads, which is here in the middle. You see this look-ahead distance, eta greater than 0, and you see also, as I mentioned earlier, that g of rho is given by the minimum of rho and the maximal density of the second road. So this is an important issue that needs to be mentioned, which is different from the modeling earlier. So anyway, for some initial data of bounded variation again, where we have that the initial density is bounded by the maximal densities of each road and some hypothesis on the velocity functions vi and the kernel function. So this is now the thing you asked for. So this is given as an hypothesis here. In this framework, we are again able to show that the Cauchy problem to this problem has a unique entropy weak solution. And let's say the proof is clearly the same as before, but with the difference that we have to adapt the numerical scheme to this one-to-one intersection. It's like a more technical component to extend everything, but the ingredients are the same, and we can really derive the right estimates for the well-posedness here. So let's go to the numerical examples to show you again the ideas of what happens in different situations. Okay, we consider two roads, initial data provided in this way. So there's a jump in between, a final time of t equals 1, a linear kernel function now given by this relation here, and eta should be 0.1. A linear velocity function as usual given in the traffic flow network like this, and the parameters for each road, which should be some bounded density by 1 for each road and different maximal velocities for road 1 and road 2. Okay, so what does it mean now? Let's consider the first example and maybe the picture here on the left, which gives you the results when Vmax from road 1 is smaller than Vmax from road 2 for this type of Riemann problem here given as initial conditions. And of course, since the maximal velocity on the second road is larger, you see that the traffic jam is resolved in that way. Okay, so the cars propagate to the right, and then at the intersection there is a small change, and this is the solution we are able to compute. Okay, and in the different situation where the maximal velocity on road segment 2 is smaller than on road segment 1, so it's a reduction of speed in some sense, you see the traffic jam is resolved like this. Okay, so the cars are blocked and so on, and we observe some backward moving wave. Okay, so this is just to give an idea on how the solutions look like for the intersected model. And of course, we are interested again in the numerical convergence for eta goes to 0. And so far, as I told you, the convergence is only shown for some special assumptions, and the most important one is the monotone initial data. And there's a nice recent work by Colombo, Crippa, and Spinolo on the blow-up of the total variation in the local limit of a non-local traffic model, where they constructed a very nice example to really show that the total variation will increase, okay, when you don't assume monotone initial data, okay. So, but anyway, we tried again to do the same comparison as before in the limit, and now we need a good, or let's say a valid model for the LWR model as a comparison. Okay, let me remark that the model we proposed is in general not monotonicity preserving for velocities that are not equal, and even for constant initial data. So we are on the side that none of these assumptions will hold true, okay? So we really try to get the numerical convergence by observation again. So the proof is still missing. So, and I tried to tell you that the analog LWR model for a comparison is now a bit different, meaning that it's a model where you have a jump at the intersection for these different velocities, of course. Yeah, that's why here in this formulation, the Heaviside function occurs, meaning that you have a velocity on road 1 and you have another velocity on road 2, and the flux is composed of these two parts which play a role for the LWR model. So, and the vanishing viscosity solution to this type of equation was investigated in a work by Carlson and Towers, and they proved that the vanishing viscosity solution defines a weak entropy solution for this model here, meaning that they add some diffusion on the right-hand side with a small parameter epsilon, and then let epsilon to go to 0 and derive this vanishing viscosity solution concept.
Yeah, it was so smooth, the Heaviside function?
No.
So they could do it?
Yeah. As far as I know, maybe in the derivation of some estimates.
Okay.
Yes.
You don't need much. If you smooth it, yeah, okay, yeah.
That's why they added the diffusion on the right-hand side.
Yeah, then you can
yeah. But I can check it afterwards. So, and for the convergence, we go back to this two setting I presented before, and this is just a zoom in to really show how the solution may look like at the intersection point, which is at x equals to 0, and you see here in different colors, of course, now how the solution propagates, and in the case of, where is it? for eta in green 2 times x, and in red 10 times x, and so on, you see that the numerical solutions we are able to compute are close to the vanishing viscosity solution presented by Carlson and Towers, and then implemented via a Godunov scheme again. Okay? So it seems that again, we observe some convergence, at least from a numerical point of view, but it's not clear what does it mean for this kind of model here, okay? So is it really a convergence we are able to prove in some time or not, or are there any other solution concepts, for example? So this is ongoing research. So, and the open points now is, of course, as a clear way of proceeding in this directions of networks to say, okay, now we know what happens for the one-to-one intersections, what happens for other types of intersections, for a merge, for a dispersing junction, and so on. Can we do the same modeling? Are we able to prove, again, the maximum principle, the well-posedness of solution, and so on? This is now work in progress, I would say. So far, no optimal control has been done. So is it possible to include control issues like speed limits, ramp metering, and so on, which results, of course, probably in another boundary condition for this type of problems? Open question, I don't know. So, and what's missing from an application point of view is the model validation and the calibration. It's not clear if the model, the non-local model, really covers reality. I don't know. I don't have the data to show or to calibrate parameters and so on. It's not done so far, okay, for the non-local models. And of course, there are further minor points I don't want to present here, and I want to finish now, and thank you for your attention.
Thank you very much for the talk. Are there any questions? Okay, Oliver. Should work.
Having a maximum principle is really nice for the analysis, but it's kind of troubling for the traffic modeling, because if you start with a solution which is not, if you start without a traffic jam, you never get a traffic jam. Can you somehow, how do you see this moving forward in terms of changing the equation and adapting this type of scheme for an equation which doesn't have a maximum principle?
What do you mean exactly?
I mean, the first equation you show, you have a maximum principle, so the bounds on the initial data are bounds for the entire solution. So for instance, you can never see the concentration of, if you start with a flat density, or something which is close to flat, you don't see...
Which model do you mean?
It was earlier than this, so just on the equation itself.
Okay.
Yeah.
Oh, this one?
Here we go. So your solution is bounded by the bounds on the initial data.
Yes.
Which from the traffic modeling is somehow troubling. If you start with a traffic jam, then you resolve it. But if you start without a traffic jam, you cannot see a traffic jam forming.
Why not? So you can put Riemann data on the road and then start...
Of course, if you start with the Riemann data, but you can never see the formation of a traffic jam unless you start with a traffic jam already. And somehow, this idea of having the anisotropic convolution is quite interesting. So why does this maximum principle come in, and can you change the equation to get a similar type of model with a similar type of scheme, which doesn't have a maximum principle? And this is...
Yes.
So it's the kernel.
Yeah,
Actually,
yeah.
first of the model usually like LWR.
For sure.
Yeah.
But
Don't capture all the traffic.
no, I mean, absolutely. But what is it about the kernel? This is what I didn't get. What is it about the kernel that's bringing this maximum principle here? It's not the asymmetry.
Only
Forward.
and increasing.
Yeah.
If it's not satisfying these two properties, you have oscillations
Yeah.
appearing, and then you lose the maximum.
Yeah.
So somehow the interesting kernel, which is looking forward, is what's bringing you there.
Yeah, if
Yeah.
you give more weight to someone that is far away from you,
Yeah,
and
but-
don't look at the guy just in front of you, you can increase the...
Okay, okay,
Yeah.
I see. But
Yeah.
this is not ideal, fair enough. Thank you.
Yeah. And Paula actually did some simulations for other types of kernels where you really observe these oscillations, okay? So that's why we really put the assumptions on the kernel at all times. Or going back to the first picture I showed, it's like this, okay? So the kernel is just forward looking.
That's the other interesting thing.
Yeah.
This brings you a maximum principle.
Yeah, yeah.
The problem is that if you take an increasing kernel, for example, you even lose the, I mean, you can even go over the maximal density. That's not physically acceptable.
Sorry.
Concerning the non-local to local limit, in the paper by Maria Colombo and so on,
Yeah.
they actually prove, they show some counterexample for the convergence, and they show that the Godunov shows the Godunov scheme shows the convergence in the counterexample. So you have any I don't know, any hint that this is the case also in this new model, or?
Not really yet. So we found this paper some weeks ago and went through roughly to get the main ideas, and we have observed that they put these special assumptions on the initial data and so on.
So they prove that the convergence in general is false. So they and the Godunov scheme catch the convergence. So is just I know that they are very recent papers, so I didn't expect it. So if you have any hint about some special initial data that you can easily prove that the convergence is false, as in their case, and the Godunov scheme converges. You have any?
Yeah.
Maybe it can be something interesting to
we have
explore.
to check that paper or these investigations done here more precisely, okay? So it was too recent to go through exactly, but it's going to be very interesting at this point now.
Can I have another? And concerning the blow up in the total variation, can you say how the BV estimates you get depends on eta, in which term, on the scaling parameter? Maybe I miss it. And
no, I didn't put the estimate on these slides here. I just put the estimate for the non-junction model.
Yeah, even in this.
Which was of this type here.
Okay.
And you see that eta is a component of the constant.
Okay. Okay.
Yeah. And this can be extended to the one-to-one intersection. Okay. I can show you the details in a few minutes.
Okay, well, you can see. Oh.